presentation will be given by Professor Blair Perot. He is professor and director of the Theoretical and Computational Fluid Dynamics Laboratory of University of Massachusetts. So we're very glad that you traveled from the United States.
Thank you, Frank. And thank you, Dynaflow, for inviting me. We'll start at the beginning. That'll be a good place. So this talk will be a little bit different in the sense that I'm going to drop down and talk a little bit about the under the hood, what's going on in the numerical methods part of what's going on. So I'll be talking about mimetic methods and a little bit about geophysical fluids, which of course are relevant to gas industry. So there's a bit of a renaissance going on in numerical methods, and sort of a supply and demand issue going on here where there's a supply of some nifty, interesting ideas out there, and I'm in some sense trying to generate a little bit of demand by informing you guys about what's possible to do differently than what you might have been doing before. All right, so mimetic methods, what are they first off? So again, we're talking about different kinds of methods for solving partial differential equations. One of the things we saw today is almost everybody here is doing some sort of computation. They've got different forms of numerical methods to do that. And so the first thing I want to emphasize is that a mimetic method is not a different kind of numerical method. So this figure here is basically, if you've got the space of all possible numerical methods, you guys recognize some different classes, right? So there's finite element methods and finite difference and finite volume methods, right? Different class of numerical methods. And then I'm going to tell you that a mimetic method actually overlaps with all the things that you're doing already. So when we're talking about mimetic methods, you don't need to change whatever your favorite data structure or paradigm is, right? There's a subset of pretty much all kinds of numerical methods, which are mimetic. So just a second, I'll tell you what that means. So we're not talking about a new kind of numerical method. We're talking about how to identify pieces of existing numerical methods, and the answer to this is that work better than the whole class. So we're starting to discover in the field of numerical methods that there's more, and out of the universe of all these possibilities, which you see in all the papers, there's a subset of those methods which are the good ones. Right? And I'm going to sort of try to tell you guys how to identify them. All right, so what are they? So in the beginning, mathematicians developed numerical methods, and they had these mathematical ideas about what a partial differential equation solver ought to do. And some of you guys have heard all these things. We're so interested in accuracy and stability and convergence, and these are kind of mathematical ideas. And then all these methods were sent off to the engineers like you and I to actually do stuff with them. And then we started selecting through them and throwing some of them away and keeping some of them for other reasons, right? And those reasons have to do with how well they actually solve our problem. And so I'm going to try and suggest is that now we know mathematically how to identify those methods that are going to work well before you even begin. Right, so what do mimetic methods do? I told you they're sort of a subset of what you're used to doing. And you'll notice that certain methods do things right. So the sorts of things that you and I think about when we're talking about a partial differential equation solver is that it should do things right. So you get conservation statements. Now sometimes a conservation statement is built into the numerical method, but then there's usually other things that ought to be true as well, which you can't build in, but which you would like to be true. You'd like entropy to increase, you'd like kinetic energy to be conserved, or various other things, right? And you'd like the method to do that as well, and they do. I'll show you one where wave propagation is right. So, at a minimum, we expect the numerical method not to be perfect, but at least to do the basic things right. So a wave should propagate in the right direction, shouldn't go in reverse. There's various constraints which were high. Many of these mimetic methods were identified earlier on. Things like incompressibility, right, or something you'd really like not to create mass or destroy it. It creates very odd effects that sometimes are easy to notice and then often aren't easy to notice until far too late, right? So if your numerical method is doing odd things, then it's not such a great idea. And these modes I'm going to kind of emphasize because they really are very evil in a subtle way. So it's very easy to get computations that look okay and yet actually are completely unphysical. So we're going to talk about unphysical modes in numerical methods. And mimetic methods can't do that, right? So the reason why they're called mimetic, sort of a funny English word that even English speakers don't use much, right? But that basically means to mimic, right? So that these numerical methods are mimicking not just the mathematical properties, but the physical properties of the PDE which they're trying to solve. And we're going to do that by this funny thing. I'm going to show you roughly how it's done. I know you're not mathematicians and whatnot, but some of the ideas I'm going to be presenting are a little bit counterintuitive, And this is perhaps the first one, right? So the way to get a mimetic method, the way to get that subset of the PDE solvers which work well, is to use something called exact discretization. Now I know that looks odd, and we'll talk about exactly what that means in a second. Okay, but before we go to that, let's just talk a little bit about why you guys would care so much. And in fact, it's an important breakthrough at this time because as more and more people are using numerical methods to solve all sorts of problems, the kinds of physics and the complexity of the problems are really actually quite extreme these days. And so I'm just dropping right down here to the last one. We'll work our way back up again. So what does complex physics mean? It means that often the person running the code doesn't actually know when it's wrong or right either. Right? When we put enough of these different equation systems together, it's often possible to get a solution which looks okay and sneaks through the sort of, yeah, that looks roughly right kind of look, and then actually 3 months or possibly even 2 years later, somebody noticed that can't be right? It's just unphysical. Something's not right about the solutions we're getting out. And that's a long time to have to go back and redo everything and figure out what went wrong. Right? So it's much more difficult to see what went wrong when the solutions you're getting are actually already quite complex. Some of the things that mimetic methods also solve, which you guys see a lot of, are, one of the important ones is high aspect ratio meshes. I got a little pretty sort of diagram there, but that's not even close. Actually, I think the second presenter showed the better picture, which is a real life analysis of what the ground looks like. And you get these very thin layers, right? So we're talking aspect ratios of at least 1,000, where you'd like to have the sideways dimensions measured on kilometers and the vertical dimensions measured in meters, right? So 1 to 1,000 in terms of how things are stretched. And a lot of numerical methods do very odd things at high aspect ratio. Sure, they're all tested and given to you guys with sort of normal looking meshes, and then you're going to go stretch them, and then funny things can happen. I'll show you just an example of that as well. So, and the other thing is large jumps in material properties. In the case where you're interested in sort of groundwater flow or perhaps oil flow moving through rock structures, then you get differences in the coefficients of diffusivity of orders of at least 1,000 again. Right, so you get very different, these large jumps, and again, most numerical methods haven't been developed to handle those kinds of things, and you'd like to be able to build numerical methods which automatically can handle these large jumps in coefficients and these sort of highly stretched meshes. So that's the key takeaway from this one, is that the trick with complex physics is that often nobody knows this until way too late. And what you'd like to do is build your numerical methods where it can't go wrong. And that's I guess the renaissance in numerical methods, is that we now understand how to do that, how to start from the beginning and make sure that it's not going to ever go wrong. So we're going to get there soon, and I'm going to give you some examples, some sort of academic-looking examples, I admit, to try to convince you that funny things can happen even when the problem's really, really simple. And so this is actually an example. I also wanted to highlight a lot of this work's going on in the Netherlands itself. So I know a little bit of work in France, a little bit in the United States, and quite a bit in Holland. So I was going to highlight a few of the people you might want to talk to later if you're interested in this kind of stuff. So Jason Frank had this problem, and he was interested in wave propagation. And I mentioned before that it's nice to have things propagate in the right direction. And I've even simplified the equation even simpler than wave propagation. All right, so this is advection, and all I should do is take something and move it to the right. And in this particular case, my velocity is 1. Just move everything to the right. Okay, so these little pictures here, this is a central difference scheme. And this is the x-axis. It's just 1D. It's as if you were flowing down a pipe, right? And everything when it flows down a pipe should go down the pipe. Right, so fair enough, we're going to do a little calculation like that. We're going to do it at very high time resolution, which you probably wouldn't do normally, but just to sort of prove the point. So it's flowing down the pipe, and I start with a bump at this location here. Now this axis here is time. So you can kind of see as we're going up this way, we're moving to the right because the bump is flowing downstream. So there it is, flowing downstream. And then I've done one little odd thing here. So normally, yeah, you guys probably did this way back in undergraduate days. But what I've done, one thing here is I've taken the mesh, and it goes from 150 points on the left-hand side to 50 on the right. So I've dropped the mesh resolution. We even saw a picture of this, right, where you take the mesh resolution, wouldn't it be great if I didn't have so much mesh resolution in this big section here? Right, so I dropped it by a factor of 3. So it's got 150 mesh points there, and then it's 3 times bigger here. And it's advecting along, and lo and behold, there it goes. And then you can almost see it. When it hits that interface, for no good reason, really, you can see a little bit of a light bliff coming off here. So This is the reflected wave, and it's actually managing to propagate stuff backstream in this flow. Now, I originally did this kind of calculation. I was interested in compressible flow and in real waves and things bouncing back and forth and whatnot. And we're getting spurious bounce backs, right? And you think, oh, that's because it's the complicated, compressible flow calculation and so on and so forth. No, it's just the central difference scheme, right? So there's ways to discretize things well, and there's ways to discretize things better. And the central difference scheme, sort of classic thing you would do, isn't that great. It can actually advect things backwards, strange enough. Okay, so here's a method Jason looked at as well. It was a box method, right? And this one has to propagate things forward, and he does an awful lot of math to show you that mathematically there's no way this thing can go wrong, right? So it doesn't bounce waves backwards when you change the mesh size. Now, clearly, this shouldn't happen, right? It's just a matter of changing the mesh size. You'd like to be able to change your mesh size. We saw different meshes where they're jumping at least by a factor of 2. And so this is a mimetic method. This is an example of the mimetic method. That's an example of what you guys probably have in your codes. And sometimes, in this case, it's really easy to know when it's right and wrong. But most of the time in your codes, when you have complex physics, you don't know exactly where that came from or why, right? It's just sort of things are happening, and it's hard to identify where they're coming from. Completely different example. Okay, just to give you something similar. So this guy here, I take a nice square box, of course, an academic problem, so that we can really identify that it's the method that's wrong, not any of the complex physics. So put an unstructured mesh on a box, and I'm going to solve this funny-looking equation. I know it looks odd to you guys. You might have seen it if you've done electromagnetics, but this is also what you're going to get for resonance. So if this is a funny square drum and I beat on it, right, the question is what kind of waves does it make? I want to know what it sounds like when I hit it. So it's almost a structural mechanics problem. And it's called an eigenvalue problem because you get certain modes, these eigenvalues here, lambda, and it's a nice little problem for an academic because we know the answer. So the eigenvalues come out, and these integers have to run from 0 to infinity, or that one's 0 to infinity as well. And so you can add them all up, and you get these sort of possibilities, right? So the real answer should be 1, 1, 2, 4, 4, 4, something, right? So I'm not even going to show you the solutions, the funny sort of waves that it makes when you hit it, but just the different eigenvalues that each one corresponds to. And if you do a regular finite element method, right, you just put the linear finite elements, you put the unknowns on each little node there, you put linear on each little triangle, it's all quite straightforward. And you run it and you get this continuous spectrum of eigenvalues, which is kind of odd, right? So it kind of means that you get all sorts of frequencies out of a drum, which isn't really the case, right? There's a lowest mode and then a couple one up from that. And then if you use a mimetic method, that's an example of a mimetic finite element method. I'm going to show you lots of different mimetic methods. The box one is basically control volume one, right? So that, again, it's not a kind of method, it's just a subset. So this subset of finite element methods does roughly the right thing. Is 1, 1, 2, 3, 4, 4, 5, so on and so forth, right? It looks to you guys that it's actually exact. It's actually not exact. This is a numerical method. Everything's approximate, but it converges exponentially close, right? So this one's getting there a lot quicker than this one ever is going to be. Let me show you again an example. Yeah, keep on pace here. Of why you might not have noticed this before. So. Zunk. Okay, so if I had done this on the square mesh, which is usually how things are, just generate it's a nice square. The easiest mesh to generate is this nice Cartesian one. And then lo and behold, if you had done exactly the linear finite element on this, it looks okay. It actually works right. So we're often used to using unstructured meshes and saying, oh, that will get rid of modes. But actually you can see in this particular case, and particularly with vector equations, so these here are vectors, they're bold, right? Funny things happen. A lot of numerical methods are sort of tested in the context of a nice scalar equation. This is basically a vector Laplacian. So you've all done the scalar Laplacian case, and that's easy. And the second we go to vectors, all sorts of more interesting things happen. So the opposite thing happens. And now we're getting better performance out of this one. But actually, notice this guy here at 6. 6 isn't actually a possibility. So this is still got a spurious mode in it. I warned you guys about this before, right? So this drum can actually beat in ways that are physically impossible. And you might not notice it, right? Because if you're just hitting it at the lowest frequency, you will get roughly the right answer. It's just when you get to the higher frequencies, up around 6, it'll start giving you tones that don't exist on this drum. So we'll continue on just to give you one final example of what that kind of means. So again, this is an even odder looking drum where it's an annulus, and if you hit it, you get certain modes. And I'm just showing you one of the particular modes, which is sometimes when you hit it, you get things moving, in this sort of 4-quadrant way, right? So this is actually one of those eigenmodes with 4. You can see I've taken the eigenvalue out and actually just solving for a forcing term on this vector Laplacian problem. All right, this is what happens if you do linear finite elements. This is the issue of modes and how they can really change the entire solution. So you know that this is kind of a motion in which you hit the drum and it sends a wave around and around and around the drum. It doesn't actually ever do that in real life, right? But the numerical method will calculate it and give it to you. It's being polluted by this solution here. Actually, if we dig underneath here and pull out this funny mode where it's going round and round in a circle, you'd see this buried underneath. It's just so much smaller that you can't see it, right? So these modes can also pollute what's going on in your solution and give you physics that looks kind of reasonable, but actually, if you think hard enough about it, doesn't really apply to this case. So, final one is one actually from my own research here. And so this is an entirely mimetic method, right? And then this is what actually motivated my interest in this field. So it's just a 2D oscillating droplet. We were interested in the dynamics of droplets and collisions. And then we noticed that this guy tends to drift. And there's really no reason for it to drift. It conserves, the numerical method conserves momentum and energy and everything else. And the answer ends up being that the surface tension doesn't. And the question is, well, then how do we do surface tension in a mimetic way so that it doesn't just sort of randomly start to drift? This actually causes it goes faster and faster and faster, and we were doing spray calculations with many of these droplets, and it causes the spray to disperse much more quickly than it ought to. Why? Because it's just complete numerical garbage, essentially. And the question is, how do you do a new kind of physics mimetically? So even if somebody invents a mimetic method and hands it to you, they're going to invent it for their particular equation system, right? And then you're going to say, well, I'd rather do something else. And in my particular case, I wanted to do surface tension right? Physically without modes and all that kind of stuff. So in order to do that, you actually have to know how to generate, start with any PDE and generate methods which always work well. So if you figure out how to generate surface tension mimetically, then you just program it up, and now it can't do anything but work right. It just sits there and oscillates. So this is a moving mesh code, and unlike many codes, for example, if you had a fixed mesh in the background, it doesn't do this either because you get artificial diffusion. But on this moving mesh code, there's really nothing holding it in place, right? There's nothing there, it just moves around. And that's why the other one could drift. If you get the slightest thing wrong, right, that arrow just slowly builds up in time and off it goes and drifts away. But now this one just can't even drift. And so ultimately the goal of this thing, this is the real calculations we were trying to do originally. Not that guy, but... so we're actually interested in whether these things come apart or not. There's a lot of forces at work here. There's a pinching instability where it wants to pinch at the center and form two droplets. There's rotational effects where they're trying to centrifuge themselves off, right? And then there's also viscosity and surface tension pulling them in towards each other. So the question is, at what point do ligaments come apart? So, all right, so it all sounds fine and good, and I just wanted to give you a hint, roughly, of how this could possibly be true, because I told you before that the way to do this is with some sort of exact discretization, and that should be very disconcerting, hopefully, and we'll talk about what's going on. And basically, the game plan is to completely reverse the way you guys think about numerical methods here. So, how to construct a mimetic method. So you want to separate discretization into two parts. Right? And you normally think of discretization as just turning a PDE into something I can solve on the computer, and I'm going to suggest that if you just tease it apart a little bit, you can do a lot more with it. So here's the idea. Discretization is going to be turning the PDE into a linear algebra problem, into a matrix problem, into a finite dimensional equation with finite number of unknowns and finite number of equations, but it's not square. Right? So that linear algebra problem there that you get from discretization, which we're going to do exactly, by the way, okay, is not square. Then in order to solve a system, of course, you need the same number of equations as unknowns. You need to make it square somehow. That's where you add the approximation, right? And that's where you turn it into a solvable system. So I'm going to separate the business of approximation and solvability from the business of making a discrete system out of a PDE. The good news there is that when I do that discretization exactly, all this business about knowing how to discretize a differential operator, which is this funny calculus continuous thing, goes away. We're going to do that exactly. So all my calculus is going to work perfectly. Things like conservation of energy and whatnot are going to work right because we're not going to do any approximation there. So that's what I mean by exact discretization. Pull this into two pieces and do the first bit exactly. And the net result of this is we're going to do the calculus part of the discretization and the physics part exactly. And you're going to see where we're going to do the approximation part. It's actually where you're already doing lots of approximation already. So I'm going to do approximation, and it's actually going to be in all the material laws. So material laws are things you look up in books anyway. They sort of right? So there are things like, I don't know, Perot's law for heat conduction or something like that, right? It's applicable to materials sometimes to a certain extent. And we'll put all the numerical approximations in with the material properties. So I want to give you just one example because it's still looking a little bit fishy. We'll do something really simple like the heat equation, which is about as simple as I can get. So you've got change in, and this is also Darcy flows like this too, which is actually what we were calculating. This is the flow of fluid through porous media. But I'll do it as a heat conduction example because I'm not sure everyone knows about Darcy flow. So that's how temperature changes in a solid with time. And then I'm going to pull it apart. So normally the mathematicians like to look at one equation, but I actually like to look at 4 different equations in here so that I know the bits that need to be exact and the bits that need to be approximated. Conservation of energy is important to me, and lots of numerical methods aren't going to conserve energy. And of course, that's the whole reason for that equation, is any engineer that's solving the heat equation actually is trying to solve some form of energy conservation. So I'd like that to be exact. I also got this guy here, which is this gradient, and that's the other bit that's got math in it and whatnot, and I'd like that to be exact as well. So then I have to worry about funny things can happen with gradients. We won't go into the details because we're definitely moving on time. Okay, so there's the physics and the math and the bits you want to be right. They're the bits that you used to look at and say, wow, that's the hard bit. That's got differential operators in it. I got to do that approximately. And we're going to do that bit exactly. And then here's the easy bit coming up. Okay, the heat flux is proportional to the gradient in the temperature. That looks really simple. It's just multiplied by a fudge constant. It's just an algebraic equation. This is where I'm going to put the approximation. Perot's law is not exact. It's something invented by engineers to solve problems, right? So I'm just going to put the numerical approximation in with the engineering approximation for how materials behave. And there's another one called perfectly caloric material, which is how you relate internal energy to temperature. And again, with some fudge constants you look up in a book, density and heat capacity. Right? So those guys are actually the ones, the material approximation, that's where all the approximation goes. Now, that's completely different from the way you thought of numerical methods before, I think. Probably you thought the first one needed to be approximate and the latter ones were dead easy. Right? And we're going to switch it up. And when you do switch it up, you get a mimetic method. All right, so we'll try to make it fast. Now we're going to discretize and I'm going to do it exactly. If you use a lot of integrals everywhere and define all your unknowns as integrals, so I've integrated both in time and space, that first energy equation. And some of you guys have done this before. This is a control volume method, basically, right? Then I get an exact expression. All I got to do is define all these nasty integrals as quantities I'm interested in. So the trick here is that the reason why I can take an infinite number of equations and unknowns, which is what a PDE is, and turn it into a finite number of equations and a finite number of knowns, but still do it exactly, is because I collect up all those unknowns into a quantity, an infinite quantity into one, right? An integral is you collect up a whole bunch. But certain collections, right? So you got to get the right collections in the right places. And the equation tells you which collections to go get, right? So I have integral quantities on those things. So I've got the internal energy integrated over volumes and sums over fluxes and all that kind of stuff. It's all kind of common stuff to you guys. What makes this discretization different from what you've done in other control volume methods is actually the second guy here, which I'm going to do the gradient exactly. So if you integrate the gradient over any line, the fundamental theorem of calculus tells you it's equal to the value at the 2 endpoints. So that's also exact, right? It just tells me where my unknowns are, and I get another exact equation, right? So I've just done those 2 equations exactly. Now here's the bit I warned you about is, of course, these guys are completely independent of each other. Somehow these are exact equations, but I can't solve this system because somehow internal energy has to be related to temperature and heat flux has to be related to the gradient. And what's most important is when you do this, you notice that they're never in the right place. I've got things at nodes and things averaged over cells and things at faces and things at edges. And what it all boils down to is an interpolation problem. So I've got a little figure down here on the right. We'll get to that in a second. So that's numerically exact bit. Here's the approximate bit. So now I just have to relate these guys to each other. They're just arrays of unknowns now. So it's much easier to figure out than partial differential equations. It's just linear algebra, which is sort of simpler. I've got one array and I have to relate it to another one. Well, there's some matrix that relates them, right? And you get to decide what it is. And that's how all mimetic methods differ. they all differ in how they go about figuring out this thing. So if you're a finite element guy, you go figure out this matrix a different way than a control volume guy will. So I'm going to leave that up to whatever your particular love or flavor is of how to do interpolation, right? And then we're going to, just as sort of, the easiest one is a diagonal matrix. You just multiply it by its stuff. So for example, we've got heat flux along the faces here, but gradient along the edge there, and I got to convert one to the other. It's a matter of geometry, multiplying by areas and dividing by lengths and putting the conductivity in, right? It's basically an interpolation problem. So that's the numerically approximate bit, which looked easy before, but actually is hard in real life, because in real life we are dealing with discrete systems, and they're never actually in the same place. So you can see why it looks so simple at the mathematical level is because at the mathematical level, everything shrinks down to a point, right? And then it doesn't matter, all meshes go to the same location. But the second we actually try to deal with the finite, things aren't actually in the right place, and you have to do interpolation. So here's the key piece to that whole thing. Another way of thinking about it is when you do mimetic methods, you invariably in some way end up with things on two different meshes, and your entire problem is interpolating between the two. So when we do the energy equation, I was integrating, it was actually a polygon kind of method, right? A control volume around that polygon with the sum over the fluxes on the faces of the polygon. But then when I did the gradient exactly, which is the uncommon bit for this kind of thing, then it ends up being along these lines of the original triangles, right? So one is sort of an equation on the green triangles, and one is an equation on the magenta, purplish kind of polygons, and they're not the same places. And then, of course, in order to actually solve the system, you have to end up connecting those two different meshes and things at different places. So how does the node value relate to the volume integral? And how does the face integral along here relate to the integral along the line there? So one key thing, again, is to remember that your primary unknowns in mimetic methods are always integral quantities, and you're trying to relate them to each other. We tend not to do that. We tend to love to think about point values for everything everywhere. And when you do that, you lose track of what you really should be thinking about, which is these integral quantities. So almost there, just one final result to sort of see what you get when you do that. So I'm going to solve that heat equation on this sort of interesting, funny camshaft case. I'll fix the temperature at the two ends and see what happens, and then have a good look at all the errors and things like that. So my favorite plot actually involves the cost for a numerical method versus the error you get, because that's what I really care about, right? So for any particular error, how much is going to cost me, which method is better, and so on and so forth. So there's a real difference. Here's the two different mimetic methods. One is putting the unknowns at the nodes, and unknowns putting at the polygons, if you like, and then you could redo the whole thing and switch it around and put the unknowns at the triangles, and the other guy ends up being on the polygons, right? So you flip it completely around. You get two different methods. They're almost the same sort of price and cost when it ends up being with the L to error norm. Now, if I had done it here versus delta x, one of these would have really won, because there's actually a lot more cells than there are polygons. Triangles and polygons are not the same number of them. But when you just look at the cost, so you kind of want to be as low down as here as you can, right? You want as little cost for as little error as you can. So these guys here, those would be the best methods if you'd like them. Roughly about an order of magnitude less cost for the same error, or less error for the same cost from a regular control volume kind of method. I did want to point out, I put one more on here, up here, which is also a mimetic method. So they don't always come out better, right? Remember, the point of the mimetic methods wasn't really just to get the cheapest method for the value. It was really to get the physics right. So there's a lot of sort of thought that, well, this also has to give you a better method. This one actually is more expensive. This is actually the box scheme that you saw convex things properly through jumpy meshes and things like that. So it's not always better, but it always gives you the right physics. These are all the same order of accuracy, so they're all second order accurate methods. But of course, order of accuracy doesn't tell you a whole lot about what the method really, how it really performs. So some of these are really an order of magnitude better than others in some sense. So yeah, look at that log scale. So summarize it up. There are some real interesting developments in numerical methods going on. Again, I kind of wanted to highlight that to you guys so that you knew what to ask for. If you don't know that there's a great new engine for your car, you won't ask for it, and this sort of highlights that it's out there. A lot of it's happening here in the Netherlands, and there's, I guess I mentioned one name explicitly, but I think possibly on the slide there was another one. So Mark Gerritsma at TU Delft is also working on all this stuff. And then these methods, I just, again, wanted to highlight that more complex your physics, and that's kind of why I thought this audience was a good one, because I view your physics as actually extremely complicated, right? The more important it is to actually get the thing under the hood working right, so that you don't have to worry about it giving you funny answers and not noticing it until it's too late. So with that, I'll take some questions.